Hello everybody. Today's lesson takes a look at the definite integral as an area bound between a curve and the x-axis. Before we get started, I want you to know we're starting with the back side of your note sheet, and we're going to look at the integral notation. When we integrate some function from a to b, a tells us the starting point, or in other words, the starting x value. That is, if you're integrating with respect to 2x. And then b tells us the ending x value. Provided we're integrating with respect to x. So today when we talk about the integral of f of x from 0 to 1, we want you to be sure to know what that means. The integral from 2 to 5. Okay, so let's get started. We'll look at this graph and we'll look at some of these problems together. If you take a look at problem number 1, you see that we're asked to integrate from 4 to 4 f of t dt. So let's go on the x-axis and find where this is. 1, 2, 3, 4. So our rectangle or trapezoid or whatever shape we're dealing with is going to start at x equals 4 and it's going to end at x equals 4. So we didn't really draw a rectangle. If you think of the area of that rectangle, the base of the rectangle is 0 and the height of that rectangle is 1, and 0 times 1 is 0. Therefore, the integral of f of t from 4 to 4 is 0. And that's going to be one of those properties that you're going to see from time to time. If you integrate any function from 4 to 4, or from 3 to 3, from any x value to the same x value, that integral is going to be 0. Now let's move on and look at problem number 2. We're talking about the integral of f of t from 0 to 1. So if you look at the graph, we're going to start integrating from x is 0 and go to where x is 1. And we want to find the area under the curve of this region. Now you might notice that we have geometric shapes, and we're not really going to do any integrating in calculus today. We're going to lay the foundation with some calculus concepts. Okay, so finding the area of this rectangle. The base of the rectangle is 1, and the height of the rectangle is 2. So the area of this rectangle is 2. Now we need to talk about determining whether our integral has a positive value or a negative value. And let's think of it like this. If we start at 0 and we go to 1 on the x-axis, that means our change in x is a positive value. And you see that our y values are all positive values. So our base times height is a positive times a positive, which equals a positive. This integral is going to have a value of positive 2. So now let's take a look at problem number 3. Problem number 3, we're asked to integrate f of t from x equals 1 to x equals 3. So if we identify where x equals 1 on this graph, 2, 3, you see that the region defined by f of t in the x-axis between 1 and 3 is a triangle. You remember that the area of a triangle is going to be found by taking half of the base times the height. Well, the base of this triangle from 1 to 3 is 2 units long, and the height of this triangle from the x-axis to f is 2. So our area of the triangle is going to be 1/2 of 2 times 2, which is 2. The integral from 1 to 3 of f of t with respect to t is 2, because the area bound between the x-axis and the curve on this region is 2. And once again, we have a positive value, because integrating from 1 to 3, our delta x was positive, and our y values were positive, and positive times positive makes positive. So now if we take a look at number 4, you see that we're asked to integrate from 0 to 3, and we're going to look at this 2 different ways. First, let's just go to the graph, find where 0 is on the x-axis and 3 on the x-axis, and look at the region bound between f of t and the x-axis. You see we get a trapezoidal region. So the area of a trapezoid is found by taking half the sum of the bases times the height. Well, this top base has a length of 1, and this bottom base, its parallel side, has a length of 3. And the height is going to be the distance between the parallel bases, and the height is 2. So the area of this trapezoid is half of 1 plus 3 times 2, which gives us 4. The area of this trapezoid is 4. Now, we could have thought of this problem a little bit differently and arrived at the same answer. If you remember, back in problem number 2, we found that the integral from 0 to 1 of f of t dt was 2. And we found that the integral from 1 to 3 of f of t dt was 2. Well, since we have the same function, integrating from 0 to 1 and then from 1 to 3, finding the sum will give us the total integral from 0 to 3. And you see that 2 plus 2 is 4. This might be confusing now. This principle will make more sense as we do more problems and look at more graphs. So continuing on, I'm going to ask somebody to pause the video right now. Why don't you guys try to do number 5 on your own and then play the video before going on to number 6, because number 6 has a little bit of a trick that we should go over together. So pause the video, try number 5. Good luck. Okay, so you've had a chance to try this. Let's check it out. The region we're dealing with is bound between the function f and the x-axis. It's the shaded region we see down here. And let's go to work. Going from 3 to 6 on the x-axis, our change in x is positive 3. So the area of the triangle is going to be half the base times the height. So the base is 3. And going from 3 to 6, well, we have a positive change in x. But right now, you look at the height of the triangle, and the height of the triangle is 1 unit. So the area is going to be half of 3 times 1, or 3 halves. This is our area. But you want to be careful, because if you notice something different about the y values now, they're negative y values. So we have a positive change in x, but a negative change in y. Therefore, the integral is going to be found by doing 1/2 of 3 times negative 1. Therefore, the integral of f of t dt is negative 3 halves, or negative 1.5. So you can have a negative integral. Obviously, the area is not going to be a negative area. Just like you can have a negative velocity, but your speed is always going to be positive. An area can be negative, just like a velocity can be negative, but an area must be positive. Just like speed must be positive. I don't know if I misspoke right there. Okay, now we're going to go over number 6 together. We're talking about the integral from 6 to 3. So if you notice, the starting value they give us this time is 6. Start here. And the ending value is 3. We're going to end here. So going from 6 to 3, we're going from right to left. Our change in x values is going to be negative. When you move from right to left, you have a negative change in x. And then we have negative y values. So let's compute this integral. Our change in x is negative 3. Our height, change in y, is a negative 1. Half of negative 3 times negative 1 becomes positive 3 halves. So the exact same region produced one positive integral and one negative integral. Depends on how the limits of integration are arranged. You want to keep this in mind as we progress through the practice problems. Okay, take a minute if you need to. Pause the video whenever necessary. Let this sink in. And when you're ready, we'll continue with the next set of problems. Okay, in problem number 7, we're asked to integrate from 0 to 6. So x equals 0 is at the origin, and x equals 6 is here at the end of the triangle. So let's piece together a few things that we've done before. The area of this yellow shaded region, the trapezoid shaded region, we computed earlier, and we found this area to be 4. And then we computed the area of the shaded region that's green, below the x-axis, and we found that that area to be 3/2, or 1.5. Now keep in mind, if we're integrating from left to right, our change in x is positive the whole way. So the integral for the yellow region is going to be positive 4. You have a positive change of x and positive y values. But your integral for the green shaded region is going to be negative 1.5 because we have a positive change in x and negative y values. So to find the area, we use our regular formulas, but to find the integral, we have to take into account which direction we're going, left to right and up and down. So the combined integral value is going to be positive 4 and negative 1.5 put together. So 4 minus 1.5, or 4 plus negative 1.5, however you think of it, which is positive 2.5. If you prefer fractions, you can call this 5/2. But we've computed the integral from 0 to 6 by looking at the region that has y values above the x-axis and the region that has y values below the x-axis and combining their integral values. In other words, the integral from 0 to 3 plus the integral from 3 to 6 equals the integral from 0 to 6, because we're dealing with the same function. Saying the integral of the yellow part plus the integral of the green part equals the total integral. Okay. So 4 plus negative 1.5 equals 2.5. This is our thought process. Okay. Now let's take a look at problem number 8. We're dealing with the semicircle. Okay, problem number 8 is dealing with this semicircle, the half of a circle that appears between x equals 6 and x equals 10. Well, we can see that the diameter of this semicircle is 4, from 6 to 10. That's a distance of 4. So the radius of the semicircle is 2. We need to find the area of the semicircle. So the area of the semicircle is going to be pi times radius squared. And since it's only half of a circle, we're going to cut this in half. Half of pi r squared. So the area is simply 2 pi. Now, let's determine if this integral is going to be a positive 2 pi or a negative 2 pi. As we move from 6 to 10, our change in x is positive, and you see that all the y values are positive. So positive times positive is positive. This integral is 2 pi. Okay, now, why don't you pause the video and you guys try numbers 9 through 12 on your own. When you're ready, press play, and we'll discuss the answers, and hopefully all agree. So pause the video and play when everybody's done with number 12. Good luck. Okay, hopefully we all agree. Number 9, the integral was negative 2 pi because our change in x was negative and our y values are positive, giving us a negative integral. Number 10, our integral is 2.5 plus 2 pi. We added a positive 4, a negative 1.5, and a positive 2 pi. Number 11, we get a negative 2.5 minus 2 pi because it's the exact same area that we had in number 10, but we're going from 10 to 0. Our change in x is negative, making everything the opposite value. And then number 12, we go from negative 1 to 0, which is from left to right. A positive change in x, positive y value, so we get a positive value. We find the area of the trapezoid, it's 3.5. Hopefully we all agree. If you need to, pause the video, talk to each other, and help each other straighten this out if there's some confusion that needs to be addressed. Go ahead and press play when you're ready to continue. Okay, looking at the next few problems, why don't you try number 13 through 15 on your own, and then we'll check the answers together, and then we'll go from there. We're definitely going to go over number 18 together, but try 13 through 15, check your answers, have discussions if you need, and then we'll continue. So pause the video now and press play when you're ready. Here are the answers. 13, our integral is 11. 14, the integral is negative 11. And for 15, the integral is negative 1/2 or negative 0.5. Go ahead and pause the video, discuss these as needed, and then do 16 and 17 on your own. We'll come back together for number 18 and do that one together. So pause the video, do 16 and 17, and play when you're ready to check the answers. Good luck. Okay, checking the answers. For number 16, we get 10.5, and for number 17, we get 13 plus 2 pi. Hopefully we all agree. Now we're looking at number 18. There's a couple different ways to think about number 18. We'll talk about an informal way first, and then we'll talk about a more formal way. Hopefully you'll understand both. Okay, number 18, we're talking about going from 0 to 10. And we're talking about taking the absolute value of the integral. Now I want to just point out something. Taking the absolute value of an integral is a little bit different than taking the integral of an absolute value. And the way you look at this is going to be a little bit different. So number 18, they want us to take an integral and then take the absolute value of that integral. So let's first find the integral from 0 to 10, and whatever answer we get, we'll take the absolute value of it. So the integral from 0 to 10 is 2.5 plus 2 pi. So now what we need to do to take the absolute value of this integral is just take the absolute value of our answer. Well, the absolute value of 2.5 plus 2 pi is still 2.5 plus 2 pi. So even though the absolute value bars make this problem look tricky, it's really no different than the work we did before when we integrated from 0 to 10. Okay, in the next few problems, we'll look at a few other examples, and we'll clear up how to deal with absolute value bars in integral expressions. Okay, in problem number 19, now we're asked to find the integral of the absolute value of f from 0 to 10. I've shaded the regions in yellow where we have positive y values and the regions in green where we have negative y values. Remember that the area that we found for this very first region was 4. The area that we found for this second yellow region was 2 pi. And the area of this green region was 1.5. Now you remember that the integral of this first yellow region was positive 4. The integral of the green region was negative 1.5. And the integral of this second yellow region was positive 2 pi. So if you want to find the integral of the absolute value of f, all you need to do is look at each piece and take its absolute value. So the absolute value of 4 is 4, plus the absolute value of negative 1.5 is 1.5, and the absolute value of 2 pi is 2 pi. So you add these together, and the integral from 0 to 10, the absolute value of f of t is going to be 5.5 plus 2 pi. So for finding the integral of an absolute value, you look at each region independently, take the absolute value of each value, add them together. Okay, why don't you try number 20 on your own. Pause the video. When you're ready to check the answer, press play, and we'll see how you did on number 20. Okay, for number 20, we can see that the integral is going to be 13 plus 2 pi. If you look back at problem number 17, we saw that the integral from negative 4 to 10 was 13 plus 2 pi. And in number 20, all we had to do is take the absolute value of this answer. It doesn't change anything, so we had positive values to begin with. Now we'll take a look at number 21, and we'll do this one together. Okay, we're going to do problem number 21 in steps. Starting with the results from number 17, we saw that the integral of f from negative 4 to 10 is going to be 13 plus 2 pi. So now let's think about what the next step. What does it mean to take the integral from negative 4 to 10 of 2 times f? Well, all that means is we're going to double our results. This is the same thing as thinking of 2 times the integral from -4 to 10 of f of t dt, which is going to equal 26 plus 4 pi. So the integral, let me write it down here where I have some room. The integral from -4 to 10 of 2 times f of t dt is 26 plus 4 pi. Okay. Now let's do 2 more things. Let's take the absolute value of this integrand. Well, taking the absolute value of this result isn't going to change anything because we had positive values to begin with, and the absolute value of a positive is a positive. Okay. Now there's one last thing to do, and we need to recognize the fact that we didn't get the integral from -4 to 10. We got the integral from 10 to -4. So what we need to do is reverse these limits of integration. Well, having an integral from 10 to -4, you have a negative change in x. And we remember that reversing the limits of integration gives us the opposite answer. So we're going to get -26 minus 4 pi. And this is going to be the integral for problem number 21. Well, that's the end of this video. We have one more video to watch with some problems with a little bit of different focus. So when you're ready, go ahead and play the second video. Thanks for watching. We'll see you guys again next week.